Hi guys, welcome to my YouTube channel. My name is Michael Mwansarova. We are continuing with probabilities part 4. Under this, we are going to look at continuous probability distribution. When we look at probability part 3, we looked at discrete probability distribution. And a discrete variable is one that is measured and appears in jumps, meaning you are able to identify these particular measured portions separately over time. So that makes the discrete distribution in that particular case. But for today, we are continuing to look at continuous probability distribution. What you should know is that if you look at a large sample of variables, the large sample of variables, if presented on a distribution chart, will actually end up having the vertices of the bar charts which we saw under discrete probability distribution being merged into a continuum, such that now it stops to reflect the gaps or the vertices, and it just indicates a straight line, smooth straight line. Remember very well that we did look at this particular kind of distribution chart when it came to discrete distribution variables, and I'm talking about in this particular chart. You can actually look at the representation of the various distribution over time being given in form of bar charts, which can easily be seen increasing and then reaches the peak at 7, then drops to 12. So that's what we have. Now, if we have a number of them, quite a number of them, what we see is that these vertices, which are part of the bar charts, which are representation on this chart, will merge to form a continuous line like this. Okay, will merge to form a continuous line like this, and then we'll end up having a continuous probability chart, from a discrete probability chart. Now, what can we say about this particular phenomenon is that where a continuous random variable is defined, we can say that a number of observations in the sample, if they are found to be large, then the frequency polygon on the graph of probability distribution will approximate a continuous curve, as I've already explained, shown in the figure below, which is a result of the function of x being the probability of event E, with a total area under the curve bounded by x-axis equal to 1, reflecting that in all cases the sum of probability will always equal to 1. In this particular case, if it is bounded by A and B, as we can see under this particular situation where the x-axis is the limit on the graph, then what will happen is that we can say that then it can be noted as probability of A less than x, x less than B. So that's what it means in this particular case. Probability of x such that A is less than x and B is greater than x, if you want, or x is less than B. So that's what we have. When this particular presentation is made, we can say that the probability density function, or simply probability density, is probability x, which is given such as a function is said to have a continuous probability for x defined. So that's what we have. In this particular case, we can say that variable x is referred to as a continuous random variable. So a continuous random variable, because there is a continuum between A and B, the limits or the bounds of this particular distribution. So that's what I wanted to share with you about continuous random variable in terms of how it can be reflected in the form of a shape in this particular, and then knowing that the total area under this particular curve is equal to 1, because all probabilities, the sum of the probabilities of an event is equal to 1, or probability of sum of probability is always equal to 1. So if the large sample is involved, then we have seen that the probability distribution will be presented in form of a continuous smooth line, as I can show you in this particular graph. That is what I wanted to have shared with you under continuous probability distribution. Thank you for listening. Please don't forget to subscribe to my channel and like my videos. Until next time, goodbye.